name is Kartic Subr. I'm a Royal Society University Research Fellow here within the School of Informatics in the University of Edinburgh. My research focuses on inventing approximate models for complex physical systems. In 2013, Disney started a little research group here in Edinburgh, which was very exciting to me at the time because I figured I could have access to one of the largest computational warehouses in the world for animation and especially simulating light, which is horrendously difficult because you need to simulate it particle at a time, photons bouncing around the scene and all of that. And indeed, it was an exciting place to be with lots of like-minded people trying to solve very hard problems for very cool applications. This was all very exciting, but at some point I began to wonder, do I want to invest all my effort towards just purely entertainment, or could I do something more useful with it? And at that point I began to question whether I should continue at Disney or perhaps move to academia where I might apply some of these tools and techniques to other problems. Research in an academic setting was exciting in many different ways. It brought me to this Centre for Robotics here in Edinburgh, where I had the opportunity to work with brilliant roboticists who had amassed all of this equipment that I could put to use for my research plan for the next 3 or 4 years. One of my PhD students, Tatiana, worked on robotic manipulation of liquids, something that we take for granted every day as we pour a cup of tea. This was an exciting problem in 2015. I'm not sure if it is anymore.
Of course it's still an exciting problem.
I thought you might say that.
It is an exciting and challenging problem because robots and liquids do not get along very well. But also, fluids are very complex substances, but we as humans don't even think about it when we manipulate them. So for example, think about the breakfast that you had this morning. Maybe Kartic preferred to pour himself a cup of tea. I'm from Colombia, so I prefer coffee. Maybe I put some honey on my coffee and I stirred it a little bit. They are very complex substances with very different properties. So this is very hard for a robot because they have no notion of physics. Humans are massively better compared to any robot that tries to manipulate liquids because we can adapt very quickly and robots cannot. They have to have maybe a PhD student developing a pouring strategy for 4 years, and then even after that, we're still better. If a robot is going to be in my kitchen, I don't want to be waiting for the robot to pour a cup of tea. You want to incorporate some sort of simulator that will allow them to reason about the world. The problem with fluid simulations is that they can be very expensive to be accurate. From the computer graphics community, they have something called game engines, which are designed to be very fast because when you're playing, you want the game to be in real time. However, they are only made to look realistic, but are not very physically accurate. And this is known as approximate physics. So here we're looking at one of our experiments. On the left, you see the NVIDIA Flex game engine that is being used to try different configurations of the variables. And then in the middle, you see the graph of what the robot has learned while doing that simulation. And once it has done the simulation a couple of times, it will transfer that setup for the best spillage into the real world.
So one of the key results that Tatiana achieved was proving that you could work with an approximate physics engine and do something serious with it, like actually pouring a cup of tea. One of the problems with approximate models, of course, is that they now start deviating from reality. Machine learning fits in nicely here because machines are very good at detecting patterns and making predictions. So once we've taught a machine that this approximate model deviates from reality in this way, the machine learning model then fills in the gaps when approximate reality predictions fail.
The idea would be that if a robot encounters a new liquid or a new tool, it would be able to learn how to adapt just like we do.
Robots have been around for a long time on the floors of factories. We are very familiar with the idea of robots producing cars in a pipeline. But now, as we welcome robots into our homes, approximate physics is a key element to teach them how to interact with our everyday objects.
It's really interesting to think that something that was developed for entertainment, like video games, can have such a relevance for robotics, which will for sure have a massive impact in the future. What was great about working with Kartic is that he actively encouraged me to think outside the box, to try to find connections from fields that were seemingly different to solve a challenging problem.
After the success with Tatiana on the project in robotics, I began to look for other areas where approximate physics might be useful. I ran across a biochemist who was doing protein design, who explained to me that proteins are small molecular machines that act much like robots, although at a very different scale. Together, we began looking at proteins, trying to see if approximate physics might be useful in designing proteins for specific applications, such as binding to a virus to incapacitate them. We have barely scratched the surface of how to design proteins effectively. I believe that approximate physics, coupled with machine learning, can accelerate the design of these miniature marvels to tackle important problems such as drug discovery and sustainable food production.
What's really fascinating is how bringing these two areas of cognitive science and robotics together, it's sort of like an introspective process of paying attention to the details and how amazing our brains are, to try to distill that knowledge not only to machines, but to make a better society.